Hi folks. We're going to talk about an object that rolls but doesn't slip while it's rolling, as opposed to something that does slip while it's rolling. And that would be like, I don't know, imagine bowling, right? You've been bowling, right? So when you can take a bowling ball and kind of shove it, and the oiled up bowling lane is nice and slick and the ball's smooth, so the ball will slide along and eventually start to roll. This is different from that. We're saying, like, take like a basketball in a parking lot and you roll it. It's not going to slide along the ground. It's just going to roll without slipping. Okay. We're going to talk about the motion of an object like that and what has to be true. Well, this little diagram here shows you that two things happen when something rolls without slipping. One is, this thing is the ball. It moves. The ball moves from here to here. The ball translates. It covers this distance that we can call, I don't know, well, how about this? We'll call it a change in position of the center of mass. It's a vector, so I should draw it. Well, how about this? I'll actually draw the vector. The center of mass moves from here to here, right? That's a delta x of the center of mass. Well, the lines here are supposed to show you that this object maybe obviously also rotates, and the lines maybe are hard to maybe recognize, but watch this. So look, like here's the object, right? And as it translates, it rotates, right, until it gets to this orientation. But it doesn't only rotate, right? It doesn't rotate in place. What it does is translate as it does that and gets over here. Okay, so that's what this diagram represents, right? Fine. So this thing also rotates through some angle that we'll call delta theta. All right? So these two things happen at the same time, and well, let's look at this. Let's imagine that we had painted in our nice orange color. I love the orange. Let's imagine we had painted this part of the wheel, the ball, whatever this round object is. If we had painted that orange and the paint was nice and fresh, and here's the paint still, well, what would happen is this part of the ground would be painted that color. Yes? So that delta x of the center of mass is actually equal to this arc length that we can call S. So delta x of the center of mass is equal to that arc length, which is, well, let's say that this ball has a spatial radius capital R. Well, that arc length is R times delta theta. Agreed? Sure. Now, we can talk about the speed at which this thing moves, or its velocity. We can talk about the velocity of the center of mass, VCM. That's delta x over delta t. Well, delta x, we've said, is this, r delta theta over delta t. And then, hopefully, maybe we recognize, oh yeah, look at this. What's that? Well, that's the angular velocity of the object. The angular velocity of the rotating object. So we can write this VCM as capital R omega. So that's well, kind of the fundamental definition of or the fundamental criteria for an object that rolls without slipping. That its center of mass must move at a speed equal to radius times omega. All right, now we can also say, as this thing rolls, as this thing rotates, well, hold please. There are really two kinds of motion that happen. One, as we said, the object translates. It moves from one place to another. And what that means is that if we take any and every place on this object that's translating, moving along a path, well, every part of this object moves at this speed that we can call VCM, right? The object moves along a path, and every part of it moves at the same speed translationally. Agreed? Sure. Now, this object also rotates, and we can say that it rotates about its center, right? And it's, as this thing is translating to the right, it means that the rotational motion has to be in that direction. And so if we look at the motion of, well, the rim at least, relative to the center, this part is moving that way. I'm going to call that VT of the rim. And this part moves that way, VT of the rim. And this part moves that way, VT rim. This part moves that way, VT rim. Not trim, VT of the rim. Okay? Now, what do you know about the tangential speed of an object or a place on a rotating object? Well, that tangential velocity, VT in general, is related to angular speed omega. So this thing is rotating with some angular speed omega. The tangential speed of any location is, quote, r omega. Well, VT of the rim is therefore the object's actual spatial radius, r, times omega. So, well, look at this. We've got that the center of mass moves at speed r omega. We've got that the rim, everywhere on the rim, moves at speed r omega. So watch this. Well, that means since VCM is r omega, and VT rim is r omega, well, here we can say, how about this? The total velocity of each location, and I don't mean every, but some at least. Well, what we do is we add the vectors, we can add these VCM vectors and these tangential velocity vectors. So look, at the bottom, we've got a VCM this way. We also have a VT rim that way. And guess what? The sizes of those are equal. And that means that the net velocity, we'll do this in a different color, the net velocity of the point of contact, and that means this location where it's in contact with the ground, well, is 0. And that means that the bottom is not moving relative to the floor. And that means, yeah, that the object doesn't slip. So this, by definition, means V of the point of contact, and I'll say relative to the floor, is 0. Ding, ding, ding. That's what it means to roll without slipping, that the place that's in contact with the floor isn't moving relative to the floor. And why is that? Well, it's because the center of mass speed and the tangential speed are the same thing, but they point in opposite directions. Okay, so what you have to be able to apply when it comes to some, well, problem-solving situations is that you have to be able to apply or relate the center of mass speed of an object to its angular velocity. And that's how you do it. Now, we could also do things like if we want to look at the velocity of different locations, look, well, the top, is moving that direction in terms of center of mass motion. The top is also moving that way in terms of tangential speed relative to the center, VT rim. So that speed up there is the sum of these two vectors. It's 2r omega. Or it's really 2 times the center of mass speed. This place here only has a VCM because there is no rotation, there is no tangential speed of the center relative to the center because r at the center is 0. Right? At this location here, look, tangential speed is upward, and center of mass speed, I'll get rid of this one, center of mass speed is VCM, and so this place has a velocity like that. That Pythagorean theorem says is radical 2 times the center of mass speed. This place here is moving downward, but also to the right. So this place is doing that. So different locations on a rolling object instantaneously are moving in different directions. Right? If you were to look at one point, like say that point, as this object is rolling across the ground, well, what we're saying is at that instant, that object or that place is moving this way, right? Yeah, it is, because the whole wheel is moving to the right, but this place is on the quote on the way up as this object rolls. Okay, so here's the main point, folks. This is really the main point, right? If you're a get down to brass tacks kind of person, all right, the definition of an object that rolls without slipping means that the point of contact can't move relative to the floor. That means not slipping. And why is that the case? Well, that's the case because we've defined VCM in terms of omega. Well, that also happens to be the exact tangential speed of a rim, or of any place on the rim. And when those two things are equal, yeah, the net velocity is 0. Okay, it doesn't mean the object's not moving. It means that the point of contact is not moving relative to the floor. Okay, so here is what you will apply when we talk about objects that roll without slipping. That is what I call the roll without slipping criteria. That's it. All right, folks, thanks very much.